So this class is going to be about causality from a particular perspective, and that's going to be a graphical modeling perspective. This is in contrast to causality from more of a potential outcomes perspective, which is more maybe what's taken by statisticians. There's kind of a divide between the graphical modeling side and the potential outcome side. It's been coming together over the past few years. This isn't going to be too opinionated. You know, we're still going to be able to talk about some of the stuff that you might think about in potential outcomes, but this is really where I'm coming from and where a lot of the questions that we're going to cover in the class are, that's kind of the community that you're going to find working on them in the literature, the people that work on this from the graphical modeling perspective. In the class, we're going to cover 3 active areas of research within causality. So the first is going to be what I would call policy evaluation. And this is going to be mostly in lectures 2 and 3. And the setup for policy evaluation is that we have a known causal model of our system. So we think ahead of time, you know, I'm trying to evaluate what the effect of giving a specific treatment to a patient is on some outcome that I care about, like longevity. And I kind of know that the treatment is going to be upstream. It's going to be a cause of that outcome. It's not going to be the opposite where the outcome is causing the treatment. And then there might be some other things like baseline patient covariates, things like their age or their gender that might be influencing both what treatment they're going to get as well as what that outcome is going to be. This is to contrast with something that we're going to cover in the next 3 lectures, which is structured learning. And this is really where a bulk of my research has been, and we're going to spend 3 lectures on it. There's a ton of stuff there to cover. With all of these, we're only going to be hitting kind of the tip of the iceberg. But I guess the difference here is that we don't know the causal model. So we actually want to take in data from the system of interest. A lot of times I'm going to be thinking of something like a gene regulatory network. So we take in gene expression data, and we just see, okay, like in this cell, these genes were expressed a certain amount. Can I tell that gene A is upstream of gene B or gene B is upstream of gene A? Maybe I can add in some data, some gene edits to be able to determine that. And we'll talk about how we can determine structure from data in that section. The next kind of complication, though, is that when I'm talking about that, I'm saying, okay, we have these genes that we're measuring, and we know our causal model over the genes are going to be something like gene A causes gene B. It's not really going to make sense for something like images. We're not going to say, okay, this top left pixel causes the pixel next to it. So what we're kind of implicitly assuming in structure learning is that we at least have known variables. And of course, we're also going to be assuming that in policy evaluation as well. And a lot of recent research in kind of the space of causality has been trying to move away from that and learn causal models over things like images, where the kind of variables that you immediately see aren't the variables that you want to form a causal model over. So what you want to do is representation learning. And we'll cover that in lectures 7 and 8. So you both don't know the causal model, and you also don't know the variables that you're going to be working with. So you kind of have to learn that representation at the same time as you're learning the causal model. So this is kind of a brief overview. Today, today's not fitting in any one of those. What's lecture one going to be about? Today I'm going to give you a bunch of definitions about kind of the main formal objects that we work with in causality. So we're going to talk about structural causal models today and things like interventions on those structural causal models and counterfactuals that you can define based on structural causal models. So before getting into the meat of the material, any questions on what the class is going to be about? Great. And feel free to stop me at any time if you have questions. You don't have to wait for me to ask if you have questions. So when we're starting to define causal models, we're actually going to start by kind of defining the variables that we're working with. So I'll first give you something that will just define the variables and won't say anything about how they're related. And we'll start adding structure on top of that, like how those variables are related. So now I'm going to give you your first definition. So we're going to have this tuple that's called a signature. We're going to denote it as this calligraphic S. And that consists of 3 items. So first, we're going to have a set X of what we're going to call the endogenous variables of the system. So these are usually going to be like the variables that if we get some data, we're kind of observing these variables. These are kind of what we're going to be considering as like our causal variables. But we'll see in the formal definition of structural causal models that we're not going to directly kind of define randomness on these variables. The randomness is going to be derived from randomness over another set of variables. And that's going to be the set calligraphic E, which is going to be a set of exogenous variables. And then finally, for each of these variables, we're going to want to know what kind of values they can take on. So we're going to have a range function. It's going to be calligraphic R. And that's going to map variable V, which can either be an endogenous variable or an exogenous variable, to its alphabet. RV. So often we're working with things that are like continuous valued, like what dose of a drug somebody is getting, or something discrete valued, like 0 or 1, whether or not they got the treatment, 0, 1, 2, 3, or 4, like which of 5 treatments they got, something like that. Kind of abstractly, you could consider all of this formalism with the alphabets being more complicated objects. You could think of vectors. You could think of functions even. But in the back of our mind, we're pretty much just going to be thinking of discrete and continuous valued things, kind of like we normally are in the course of most kind of probabilistic systems. And as an extra piece of notation that's going to be helpful for us, we're just going to abuse notation on this range function. And if we take in, I can't really do bold, if we take in a set of variables, this really needs to be kind of like an ordered set, or like a tuple, then the range is going to be just the product set of all of the ranges of the variables in that set. So just going to be the product set of these individual ones. Okay. Any questions about the definition of a signature or that notation to extend the range operator, the range function? So let's go with an example. This is kind of going to be one of our running examples throughout the class, at least this lecture. So what we're going to be thinking about is this experiment where I've genetically modified some mice. So I'm going to have x1 is going to be a binary variable that indicates whether I modified some gene. So x1 is in 0, 1. And here's where kind of this distinction between the exogenous and the endogenous variables come up. So whether or not I modify it might be based on something like a random noise generator on my computer, where maybe I'm sampling my noise from like the unit interval 0, 1. So I can have different alphabets for the endogenous and the exogenous variables. Okay, and then if I do this genetic modification, maybe the way my experiment is set up is that I'm going to be genetically modifying 2 mice. So we'll call these mice Mickey and Minnie. Let's say this is weight in grams or something. X4 is going to be the weight of their child. Their child's name is going to be Cheddar. And X5 is going to be the weight of their grandchild. So Cheddar's child, Gouda. And all of these are going to be real valued. You could say like positive real valued if you wanted to be super specific. All of the epsilon 2 through epsilon 5 are going to be real valued. Here, I'm going to be taking the same number of exogenous and endogenous variables, and they're kind of going to be paired. We're going to see that that's like not strictly necessary. The way that I defined it up there didn't say anything about them being paired. That just happens to be our example here. So on top of a signature like this, we are going to want to add some graphical structure that describes how the variables, this endogenous and exogenous variables, are related to one another. So we'll use some standard notation from graph theory. This is for directed graphs. So if I have a directed graph G, let's already make it an acyclic graph. So I never have a cycle like x1 to x2 to x3 back to x1. I only have, I'm able to put the nodes of this graph into a consistent like topological order where the things earlier in the order are strictly always upstream in this graph from things downstream. So this is going to be an acyclic graph. It's always abbreviated DAG. Then some of my standard terminology is going to be things like the parents. So let's say this is also over these nodes. Calligraphic X, say xi is one of the nodes in this graph. This is going to be the parents. So these are just things with an arrow directly into xi. So if I had this graph, then these would be the parents. I'm not going to give examples for all of these because this is pretty standard terminology. Children is going to be the things with an arrow from xi into those nodes. And then we'll use things like ancestors, and descendants. And then it's also going to be helpful at times. All of these we're going to extend our notation where if we put a bar on top of this set, then it's going to be inclusive. So it's going to be whatever those parents were of this node and the node itself. So using this terminology, we can define a specific type of graph that's kind of going to go along with this signature to tell us how the variables are related to one another. So we'll call this a DAG G tilde over nodes. And it's going to have nodes just corresponding to the variables. So this is kind of maybe also some abusive notation where we're going to use the set of nodes and the set of variables kind of interchangeably, and we're always going to have, the variables corresponding to nodes in these graphs and vice versa. So we're not, sometimes people distinguish the label of a node in a graph from the corresponding variable. So they'll use something like xi or x1 would be the node, and then, or x1 would be the variable, and just 1 would be the node. But this is just going to be a lot easier for our purposes, at least. So over these nodes, we're going to say this DAG is compatible with the signature S if the exogenous nodes are all sync nodes. So that means that the parents of the exogenous nodes are always the empty set. So this is capturing that notion of them being exogenous. They don't actually depend, in particular, on any of the system variables. And actually, the fact that they're all sync nodes means that none of them are going to be kind of related to each other. And we'll define, when we get to structural causal models, we'll see that this makes them all kind of independent sources of noise in the system. And then we're also going to call the tuple of the graph here and S a template. So this is supposed to capture the idea of, like, if you tell me the signature and if you tell me this graph, G tilde, that is going to be able to kind of serve as a template for how we want those causal variables to relate to one another. But we haven't actually given kind of the quantitative version of how they relate to each other, which is what I'm going to do now. Okay. One thing about this graph, let me just put it here, is that we're going to call this graph the exogenous graph, because it includes the exogenous variables. We also might want a graph that doesn't include any of the exogenous variables, a graph only over the endogenous variables, which is actually typically kind of what you'll see in the causality literature. They're not going to include the exogenous variables explicitly. And this is going to lead to another type of graph that we're going to call the latent projection. And this is to capture the idea that we're projecting out those exogenous variables. Or, these would also be a form of latent variables that we don't see. So the latent projection of an exogenous graph G tilde, denoted G tilde parentheses X, is a mixed graph which means it has more than one type of edge. And the edges are going to be xi to xj if xi to xj is an edge in the augmented graph. And this is only going to be for variables xi and xj that are endogenous variables. And then we're going to introduce a new edge type, bidirected edge between xi and xj, if there exists some latent variable epsilon I, or let's say epsilon k, such that epsilon k has an edge to xi and epsilon k has an edge to xj. So I'll give an example. Say that our graph only had a single exogenous variable that pointed to both of our endogenous variables. Here we're going to be seeing, I'm not always going to be using like x1, x2, x3, x4. Sometimes I'm going to be using other variables. So I'll just say, something like this. Our set of exogenous variables is a and y. Then the latent projection, so if this is G tilde, the latent projection, G tilde of x, would be, I still have this edge between the endogenous variables, but then I also have this edge. In particular, we're seeing also that you can have multiple different edge types between two nodes. So I don't just have to have a bidirected edge or a directed edge. In the latent projection, I can have both. And just a remark would be, maybe we can even add it to the definition, though this is something that you would also maybe want to show, is that this is also going to be an acyclic directed mixed graph. So sometimes we will abbreviate this as ADMG. So this is something like a DAG, but it's just saying that over the like the subgraph of just the directed edges, it's a DAG. And then I can also have bidirected edges, and that's not affecting anything. I don't count that towards whether or not this graph is acyclic. Just the directed component of it is acyclic. I guess that's pretty obvious to see from the fact that we take in an acyclic graph, and then the only directed edges that we have are also directed edges from that graph. Yep?
So in this projection, we just ignore all the exogenous variables and all the edges that come out?
Except if they introduce a new bidirected edge. But yeah, so if and I'll give an example. Let's actually go directly to the example here and build on this. So the example I have in my mind for this, and this is kind of where the motivation for like this interpretation of what x1, x2, x3, x4, x5 are. So I said x1 is whether or not I do this experiment. And then my experiment procedure is just that I'm going to genetically modify Mickey and Minnie. They're the only ones I'll directly do a genetic modification on. Mickey and Minnie, they have a kid, Cheddar, and then he has Gouda. And all of the exogenous variables are going to enter this picture like this. So they're just going to be related to the endogenous variables. And that's actually something that is special enough that we're going to have a definition for. So I think this is definition 4 in our template. This is, we will call G tilde Markovian. If the children sets for all of these exogenous variables have size less than or equal to 1. I guess if it has no children, you would just get rid of it when you do the latent projection. And then what this is going to say is when I do the latent projection, I don't get any new edges. So I can essentially just take my original graph, this G tilde, and I can just extract this subgraph over the endogenous variables. And then that's going to give me back always a DAG, because I started essentially with a DAG and I'm not introducing any bidirected edges. So I'm not going to have to use ADMGs in Markovian models. And if it's not Markovian, it's not actually called non-Markovian, it's called semi-Markovian. I guess this is to contrast with something that kind of doesn't have any of this structure at all. So if you're looking for like stuff with ADMGs instead of DAGs over the endogenous variables, kind of the keyword to look for there is semi-Markovian. Okay. So we have all of this kind of machinery talking about how these variables are related kind of in this qualitative sense. Now we want to start getting into defining how they're related in a more quantitative sense. So the idea is that for each of the variables in my system, at least each of the endogenous variables, I'm going to introduce a function kind of telling me how that variable takes on its values in terms of the other variables. So that type of function is going to be what we're going to call a causal mechanism. So I'll start off with some template. Then we're going to say a causal mechanism. For one of the variables xi is a function it's going to be f sub xi will be a function that takes as input some realization, some value in the range of the parent set. So that's where that extension to sets of this notation helps us out. So if I have in this case, we want, say, for x4, we want a function from real values, and say real values, and it outputs another real value, so something that's in the range of that variable. And then we're going to let mech of g tilde s of xi be the set of all such functions. And that's just going to help us not have to keep rewriting, that condition on those functions. So we can just say f of xi is in that set, and that's essentially telling us that f of xi is going to be a function that takes on values in the parent set and puts out values of this variable xi. So now I'm going to have to erase for a minute. This would be a good time to think of any questions that you have so far. Any questions? Just erase these in order as I need them, so you can have it for as long as possible. All right, so now we're going to tie all these together, and we'll come up with, I guess this is going to basically be our main definition for today, which is going to be given a template. Then we'll call something a structural causal model consistent with this template, abbreviated SCM. We'll usually just use the notation M for model. I'm just going to leave the consistency with the template kind of implicit in this definition. So instead of writing out consistent with this template, it basically is going to be something that consists of two things. So first, we're going to want a product distribution on our exogenous variables. And what I mean by product distribution is a distribution where all of these variables are independent from each other. And then we're going to have an indexed set. If you're coming from Python, maybe this is like a fancy way to say like a dictionary. So this is just a set where I'm kind of keeping track of like each of the elements in the set, which index it corresponds to. This is basically going to be our causal mechanisms. So f of xi for each xi in my set of endogenous variables. And I'm going to have f of xi is a mechanism for xi. So you can kind of think of a structural causal model as two parts. We have one part for the exogenous variables and one part for the endogenous variables. And the difference between these two parts is that over the exogenous variables, It's a distribution. That's where the randomness from the system is going to come in. And then these are just deterministic functions for each of my endogenous variables. So if we have a structural causal model with this exogenous graph G tilde, then we call that latent projection G tilde of X the causal graph. Sorry, I ran out of space there. And sometimes we'll just, if we, especially in the Markovian setting, if we're really not caring too much about this full machinery of the exogenous variables, I'll just say here, this is often denoted just by G without the tilde. That's why we had the tilde originally, so that we would have it without the tilde now that we've gotten rid of the latent variables. Okay. Now we'll see, after an example, what we can do with these structural causal models. Any questions about that definition? Yep.
What does the product distribution on epsilon look like? Is it usually like a set of distribution?
Yeah, so you could think of this as a distribution for each of the epsilons. So like P epsilon 1, P epsilon 2, P epsilon 3. And the product distribution is just the distribution I get by assuming each of those variables is independent. It's a joint distribution on the set, yeah. Okay. So sometimes we're going to be thinking like everything is kind of coming from this structural causal model, but we're going to get kind of different levels of implications from this causal model. So as soon as I define just this, what you can think of is that I have these epsilon variables. They're going to generate, did I have a graph here? So they're going to generate, like if I'm thinking of running a computer program, I draw a random sample for each one of these guys, and then I can kind of solve for what the variables x are going to be just by going down the DAG. So I can first say, okay, x1 is some function of this, x2 is some function of its parents, x3 is some function of its parents, and that's going to give me, if I take together this distribution and then kind of do this push forward through those functions, that's going to give me a new distribution on the variables x, and that's going to be unique. So that's a good thing about DAGs, is because I can go in this order, I'm always going to get a unique distribution. So that's like a one-line proof, but I'm just going to make it as a claim. There's a unique distribution implied by M over these variables x, and we're going to call that, so P of x, the entailed distribution. if I don't do anything to the causal model, that immediately implies this distribution over my variables x. I call that the entailed distribution. I write it as p of x. So for example, we had this causal graph. I'm not going to write out the epsilons, but remember they're there when we're defining the structural causal model. This might look something like this. So it might be x1. So I'll be using this Kronecker symbol. Takes on 1 if the thing in the subscript is true. Takes on 0 if it's false. So this might be, I'll do the experiment if, say, my randomly generated noise here, which is uniform from 0 to 1, is less than 0.5. So this basically just becomes a Bernoulli variable. Okay, x2, say, is epsilon 2, which I'll write the distribution for in a second, plus, say, if this genetic modification gets done, it increases the weight by 2 grams. So maybe for Mickey, I always draw my mouse that I'm going to call Mickey from a population of male mice, and maybe their weights are a normal distribution with mean 25, variance 1. Similarly, with x3 of epsilon 3 plus 2x1 will be its causal mechanism. And this could be, say, a normal distribution with mean 20 and variance 1. Okay, now I have maybe, if I don't know the gender of the child, I'm going to get, my best guess is going to be that it's a half. So just the average of these weights plus some extra noise, epsilon 4, which is now 0 centered. Standard normal. And then maybe because I don't know both of the parents for x5, I only know one of them, I'm going to guess again that it's going to be this mean, and then it's going to be, say, something, this epsilon 5 might have a higher variance, so it might be mean 0, variance 2. Right? And then I can get from this the entailed distribution. So if I'm writing this out fully, right, it takes values x1, x2, x3, x4, and x5. And then, as I said, this is just going to be a Bernoulli variable. So this is Bernoulli x1 with parameter 0.5. And then I'm going to have a normal distribution over x2. That's going to be centered at 25 plus 2x1. So x2 centered at 25 plus 2x1. Variance 1. The rest of these are going to be pretty similar. So it's in the lecture notes. Maybe I won't write this out fully. And here I'm using kind of the notation you might use for a product distribution. But because x2, x1 enters into the parameters for this distribution, it's not really a product distribution. Okay, so does that make sense, kind of how all of this fits together with the structural causal model implying a distribution? Not just one distribution. So actually, the structural causal model, the interesting part about it is that I'm going to be able to do all these kind of operations on it that are going to give me more distributions. And those distributions are going to be related in certain ways. So the first thing that I can do on a structural causal model is an intervention. We'll just define what an intervention is immediately. So this is in the notes, definition 7. We have an intervention. This is I, and this is consistent with a template G tilde S. A lot of these are like these kind of composite objects, so they're like tuples consisting of a few parts. This is trying to break it down so that each of these definitions only has like 1 or 2 parts. So here, this intervention is going to be consisting of a set xi of targets. We might call them intervention targets. These are, so this is a subset of the endogenous variables. So these are basically the nodes that we are intervening on. We might also call them intervened variables. And then it's going to be, for each of these variables, also what we do to the structural causal model kind of at that variable. So it's kind of this local action. So we're going to have, again, this index set. Of causal mechanisms. And we'll refer to those as like the interventional mechanisms or the interventional causal mechanisms to distinguish them from the original causal mechanisms in our structural causal model. So if we have an intervention, we can basically apply that to a structural causal model to get a new structural causal model. Let's get in the notes. I'll be pedantic and say these both need to be consistent with the same template. I'm not going to bother writing that out, but it kind of only makes sense to apply an intervention to a structural causal model if they're consistent with that same template. And I'm going to get a new structural causal model, which we're going to call the Interventional SCM. And denote that by pretty much always when we're going to have interventions, we're going to put the intervention in the superscript of kind of the original thing to get the interventional version of it. And that's just another structural causal model. And then we need to define those two elements. So we're going to have the same exogenous distribution. distribution. And then we're going to have, let's call these F prime, are going to be the causal mechanisms. And then these will come from two places. So if I didn't intervene on the variable, then I get my original causal mechanism. But if I did intervene on the variable, I get the one from the intervention instead. Maybe we should actually, to be consistent with that I, I'll just denote this also by Fi of Xi. And similarly, the entailed distribution is denoted P subcaligraphic X, the superscript I. So maybe a few remarks about this interventional operation. Kind of this line of the mechanism staying the same is, there's a bunch of different kind of names for it in the causality literature. You might call it invariance or modularity. So it's saying that if I'm actually not doing any intervention, if I intervene on this kind of xi variable, that's completely separate. It's not going to have an effect on the mechanism for any of the other variables. And this is going to be kind of an important property. One of the kind of consequences of that, which is important enough, I'll put it on the board, is consistency, which says that if x is not an intervened variable, then if xi, I guess, is not an intervened variable, then this probability distribution of x given its parents is going to stay the same. So this is the original version, and that's going to equal the exact same distribution in the intervened version. So this is kind of like at the level of the structural causal model, the level of these like deterministic functions, these causal mechanisms, I'm not changing them. I also add on top of that the fact that I'm not changing any of the distributions here. And I can conclude that I'm not changing any of these specific conditional distributions. So this is only holding for, specifically right now, a variable given its parents. And those are kind of like the atoms of which these distributions are built, which we're going to cover in the next lecture. We'll just see that these distributions are incredibly important for defining kind of the space of probability distributions that are consistent with the structural causal model. Okay, so we're going to talk about a few different types of interventions. Yep. Yep.
Why are you talking about probability distributions? Like this condition probability distribution
This is the probability distribution in given only the parents in G. So this is the causal model, the causal graph, not the exogenous graph. So in particular, this doesn't include the exogenous variables as parents. Yeah. So there's some randomness that you're like marginalizing over. Yeah. Yeah. That's a great question. I should have pointed out. Yeah. This is important. That's G and not G tilde. Yeah.
Do you have interventions that change the parents of
Yeah, so this was a little bit of a choice of how to present this. So when we're dealing, it's kind of weird to say, especially when there's kind of these confounding exogenous variables that have multiple, so the semi-Markovian model where we have multiple endogenous variables as children, then the kind of semantics of the intervention don't correspond to like kind of what we would want them to. Like if we say that the exogenous variables can be targets, what we can do, right, is we have a lot of flexibility to change this distribution in different ways. So like if this was like the original distribution here, then if I wanted to, say, change the variance, I could do something weird like double this and subtract 25, or times square root of 2, or like whatever you have to do. This is just kind of an annoying way of like my choice here to define it super generally, so that the exogenous variables from the start don't really have to have a single child. If you do that from the start, then you could just say that you don't have to have the same P sub calligraphic E. You could instead say that the distributions of each of the exogenous variables that don't correspond to like things that you intervened on are the same, and the ones that do correspond to things that you intervened on can be different. But this shouldn't be too limiting. It's just that technically you would have to play some tricks like that. Yeah. Okay, so when people think of interventions, maybe I'll also note that this might be called, it might be more understandable even to call this a mechanism change. When people usually think of interventions, they think not of replacing a function with another function, but of replacing a function kind of with a deterministic value. And this is going to be, that is a special case of what we're doing here. But these are kind of important enough types of interventions that we're going to give them a separate name. So the first kind of separate name in terms of interventions that's important to know are going to be called do interventions, and they'll also even have kind of their own notation. The special notation that they're going to receive is that instead of saying pxi of, say, my variable is x, I'm going to give an equivalent notation that says it basically after a conditioning sign. The conditioning sign is just notation. It's not the same thing as conditioning. So say this is, say the intervention targets of I are equal to this capital A set, and the constants that we're setting this equal to are this little a, then this is going to be do A equals A. And that's just going to be a little cleaner when we're focusing on due interventions, which will be most of what we're doing in the next lecture. Because here, you can actually, instead of saying all this setup of like, oh, I have an intervention such that the target is A and the values that I'm setting it to are this little a, that's immediately just implied from this notation. And this is the notation used by Udaya Pearl, who like basically did a lot of the machinery that we're going to see in the next few lectures. Another special type of intervention that's kind of somewhere in between our kind of most general definition. So we might also call this a soft or an imperfect intervention, just to like kind of really emphasize the fact that it's not one of these special types of interventions. But a perfect intervention, sometimes also called a hard intervention, still allows for some randomness. So it has g of xi depending only on the exogenous variables. So I cut off all the dependence from the parents, which are endogenous variables. Let me see if I have one of these graphs. So this would be something like I take out, and instead of having Cheddar be the child of Mickey and Minnie, I just replace them with another random mouse. But that mouse is still random, so the value here can still be a random quantity, instead of, in the case of a due intervention, that's deterministic. That's like, oh, I replaced them by a mouse that weighs 23 grams specifically. Great. So just be careful. Anytime you're reading about stuff that's using interventions, which of these that they're considering, a lot of what we're going to be doing in the next couple of lectures is specifically for due interventions. But then when we start going back to stuff with causal structure learning, we'll see that we don't really need due interventions. We can handle these kind of soft interventions just as well. Yeah.
So are randomized controlled trials where like someone is given the treatment just using like coin flips, so not depending on anything else, like their demographic information, that kind of stuff. So is it a perfect intervention?
That would be a perfect intervention, exactly. Yeah. Good connection. So we'll talk a tiny bit about randomized controlled trials in tomorrow's lecture, but that's kind of the gold standard for determining causal effects. Okay, so let's give an example of some of these interventions in the mouse model. So I guess we can keep that there. Yep.
So, sorry, if a new intervention that's G is constant, why is it depending on epsilon?
So a perfect intervention, a due intervention is a specific type of perfect intervention. So it has a trivial dependence, say, on the epsilons, but the reverse is not true. Yeah. Yeah. Okay. Yeah, so maybe look at the examples in the notes. I don't think they're particularly interesting. I think, it's things like instead of having x1 be equal to epsilon 1, this indicator of it being less than 0.5, maybe I intervene and say, okay, I actually am going to do the intervention with this genetic modification with higher frequency. So anytime my random number generator spits out something less than 0.9, now I'll actually do that. So this would be a type of perfect intervention. Because anytime that I intervene on something that's already a source node, only depends on the epsilon 1 or whatever, the epsilons. It's always just going to be a perfect intervention. If I instead did something like I replace Mickey with some different breed of mouse that responds more strongly, say, to the interventions and weighs more, it could be, I offset it by 5, and then it's plus this epsilon 2 still, plus instead of 2x1, I could change this to 3x1. Or maybe I could even make it depend in some, x1 is binary, so it doesn't make sense to say it depends in a nonlinear way on that. But I could do kind of anything I want with its dependence on x1 here. Yeah, and then, do interventions are going to be kind of the easiest thing that we could imagine. So this would be if we always set our genetic modification to happen. Okay. Now I'm going to do something that's a little weird, but it's going to help us a lot with some of the proofs that we're going to be working on Thursday. So I've defined what it means to basically take a structural causal model and take an intervention and get out a new structural causal model that we call the interventional structural causal model. But this is kind of annoying from like a technical standpoint that I have these two separate structural causal models. And what we're going to do here is this little trick to basically have one structural causal model that defines both my original one and my interventional one. So basically I'm going to start from signatures and work our way up again. But I'm going to do it a lot faster, hopefully this time. So if we have a template, or no, say we have a signature. S and an intervention I. And we're going to have the interventional signature, which we're going to denote S superscript I, is going to be something with these variables X superscript I, which is our original X, plus this new endogenous variable, zeta I. And then we're going to have epsilon I. We'll also introduce a new exogenous variable. And we're going to basically extend the range function so that's going to be the same range function on all the original inputs, and then we're going to extend it to also take in those two new variables as input. And these new variables are just going to be binary. Okay, so in this kind of construction, I wanted to get away with only introducing this zeta I variable. It's kind of the only thing that matters. But just to keep being pedantic, like technically you have to, or at least without introducing like a new form of terminology, you're going to have this epsilon I variable. But I would really kind of conceptualize this in your mind as like we just introduce this new variable zeta I. And we can call that something like the intervention indicator or something. And then we're also going to need to introduce a version of the augmented graph. So the interventional augmented graph. So this is going to be G tilde superscript I. This is just going to be, we take in this original G tilde, and then, so let's say just the same edges as G tilde, plus we're going to have an edge from this intervention indicator to all of the variables that are in the intervention. And because this is an endogenous variable, we're just going to give it that corresponding exogenous variable as a parent. And that's a zeta. At least it's supposed to look like a zeta. Okay, so, yep.
Very silly question, but
Yep.
is there a reason we have like calligraphic xi on one side and then zeta I, but then you use the same big epsilon I?
This is supposed to be like, it's more clear in the lecture notes, but this is supposed to be var epsilon, and this is supposed to be like calligraphic E. Yeah. Okay. So new signature, new augmented graph, and now finally we're going to get a new structural causal model. And then you'll see kind of why we're calling this like the intervention indicator. It's also sometimes useful to think of it as just like a switch or something. And it's basically going to switch on and off whether we're using like the original mechanism or the interventional mechanism. Yep. It's still just a structural, well, this is a signature still. But it's just, this is still a signature, this is a augmented graph, and then this is going to be a structural causal model. It's not a different kind of one. It's just over a different set of variables with a different set of functions and stuff. Yeah. There are kind of ways that you can think of doing it as like a different kind, where you add in these nodes that represent interventions and you kind of think about them differently in terms of maybe those are like kind of these variables that index into like different sets of structural causal models or something. I played around with doing that for these notes, but found this it's going to be a little easier because we just get to reuse. Basically, we developed the machinery for structural causal models, and any theorem that applies to that will apply to this new one. Otherwise, we'd have to prove like two slightly different versions of the theorem. Sorry? Yep. It's like it's an extra node. We're usually going to draw it out with a square instead of a circle, like we draw the rest of our nodes with. So I'll do that. It looks like today we are going to use a little bit past the hour-and-a-half mark, so this is why we have the 2 hours, but I don't think we're going to go all the way to 3. Okay, so given those two things, we can now define, I'll just call it an expanded interventional SCM. And we're going to denote it MI with a plus down here, because we already had an MI to just be like the interventional structural causal model. And that plus is going to indicate that it's kind of a super graph. It's going to be a larger structural causal model than that original one. So MI without the plus was over the same set of variables as the original structural causal model. This is over the same plus extra variables. And so we're just going to use these. It's going to have signature SI, augmented graph, G tilde I. It's going to have an exogenous distribution equal to the original. And then this is going to be product with, we're going to need to place some distribution over the epsilon I. This distribution doesn't really matter, and that's why it's kind of annoying. It's kind of corresponding to this. You could say out in the real world, like there's some distribution over whether or not this intervention occurs. Really, like this intervention occurs or it doesn't, and we'll always be using our zeta I variable as something that we're conditioning on. So we actually never really need to think about what this epsilon I variable is doing. So again, this definition is kind of for the sake of pedanticness or formality. The part that really matters is that I'm going to have these interventional distributions, or these causal mechanisms in this new model. So what are they going to be? It's going to be for any of the children of this zeta I variable. So for any of these variables, let's just put that here. So for xi and this xi, I'm going to have f xi. I'm not going to put in the arguments, but it's going to be times the indicator that zeta I variable is equal to 0 plus this g of xi times the indicator that it's equal to 1. So that zeta I is just switching off between whether or not I'm using f of xi, the original, or this g of xi, the interventional mechanism. And then, so this, if we have something that's not in the intervention targets, we'll just use the original always. And then what we need is for the, I guess, zeta I variable, we can just have it take on exactly the value of the epsilon I variable. And then this is also, so we have this augmented graph, and then the causal graph of the SCM here is going to be denoted GI plus. So for our example over here, where we're, say, doing an intervention on X2, in our model here, our expanded, I guess, interventional graph, our GI, is going to look like this. I'm going to add this additional node, zeta I, that I guess it should be up. zeta I that's apparent of just that one intervention target. If we had two intervention targets, so if we were replacing, say, Mickey and Minnie with some other mice, then it would just have two children. Okay, and the thing about this this new distribution is basically it's going to be kind of consistent with either of our observational or interventional distributions. So I think I'm probably going to need one more board before we end. So this is just going to be a claim, which is that this PXI, so this was the interventional distribution. This was like the entailed distribution of the interventional SCM without the plus. This distribution is the same as the distribution now over those same variables x if I condition on that intervention happening. So this is the entailed distribution of MI plus. So the kind of benefit is going to be that instead of working with like two probability distributions, so if we needed something in probability x, which is a different distribution, that's P of x superscript I. Similarly, we're going to have that this is the same as this distribution where I'm conditioning on this value equaling 0. So instead of working with two different distributions, I can always work with just this one distribution that's now over one more variable. That's the zeta I. And I'm always just going to be conditioning, basically, on that zeta I. All right, so that's it for interventions today. We're going to come back and see how these tools are useful tomorrow, or on Thursday. Last thing I'm going to end with is a little bit on counterfactuals. These are not actually going to appear in the rest of the course, but I thought it would be a nice payoff of seeing why we're using structural causal models instead of kind of simpler notions of causality, which only talk about the distributions and don't talk about kind of these exogenous variables. Because you can get away with a lot of the stuff that we're doing without talking about exogenous variables, but you can't do anything with counterfactuals unless you're using these exogenous variables. So what is a counterfactual? This is supposed to address questions where we think about, okay, this is what did happen. This was the factual outcome. If I went back in the past and I changed just one thing, but held everything else kind of equal, then what's going to be different? So in healthcare, you might say something like, okay, I had a patient, they came in, I gave them aspirin, and their headache went away. With this specific patient, what would have happened had I not given them aspirin? And that's a little different than this interventional question of, interventions are kind of future-oriented of if I were to give all my patients aspirin in the future, what would, the probability of their headaches going away be? It's not about a specific person whose outcome you've already seen. So counterfactuals are going to be about a specific instance where you've already seen the outcome. Something else you might think of, causality really had a big uptake with the COVID pandemic. So people would ask things about like, okay, we had in our country, or say in our state, we had quarantines go into effect in March of 2020. What would have happened if they had gone into effect in February of 2020 or April? Would there have been less or more deaths or illnesses or whatever kind of metric that you care about? And the way that we can use structural causal models to define counterfactuals is kind of similar to what we did with interventions, where we defined like this operation that took in one structural causal model and spit out a new one. We can do that, but instead the inputs are going to be different. So we'll have a set S that's a subset of our endogenous variables, and then we'll have some realization. So we'll have some value that we actually saw those variables take on that's in the range of that set. And then the counterfactual structural causal model is a structural causal model now with, it's kind of nice, it's like dual to what happens with interventions. So in interventions, we left the exogenous distribution the same. Now what we're going to do is we're going to change the exogenous distribution. So the distribution over the epsilons is no longer going to be a product distribution. Generally speaking, it's going to be the conditional distribution over those variables given the S that we actually saw. And we'll kind of see how this plays out with an example. So that's the exogenous distribution. And then the same causal mechanisms. So as an example, we don't have it on the board anymore, but with our kind of ongoing mouse example, say that you saw, say we saw like the whole outcome. So we saw all of these x's, and we're kind of considering the counterfactual based on that whole outcome. That's usually what we're going to be thinking of, like the counterfactual based on this whole outcome. You can also technically do it on a subset of variables. Say that we saw x1 wasn't done, x2 say that Mickey ended up weighing 26 grams, that mouse that we selected for Mickey. The mouse that we selected for Minnie was 20. The mouse we selected, or the mouse that was bred after by these two, Cheddar was 23, so perfectly half. And then say X5, the weight of Gouda was also exactly what, so there was kind of no noise. We can condition on all of these. We can go back and solve for what would be the conditional distribution of the epsilons. So x1 equaling 0, all that tells us is that epsilon 1, what's going to be the easiest way to write this? Basically, so I'm going to do this as a product distribution over these epsilons. And this is just to show you all what each of these stand for. So epsilon 1, all I know is that it's uniformly, my new kind of posterior update on it is that it's uniformly distributed from 0.5 to 1. Open or close bracket, I guess doesn't matter. And then these are all point masses, actually. So when I solve and I say, okay, x2 was supposed to be 2x1 plus epsilon 1, well, or plus epsilon 2. Well, now I know it's, I just kind of solve backwards. I say, okay, I had this equation. Now I can just solve for epsilon 2 and see epsilon 2 is equal to x2 minus 2x1. So in this case, this is a Dirac distribution, just point mass. Now we know epsilon 2 was equal to 1. And then all of these I designed so that the random noise was 0. And then you can do things on top of that counterfactual SCM. So you can think about interventions. So now if we want to know the counterfactual of what would have happened if x1 equaled 1 for this particular instance, for this particular experiment, then that's equivalent to doing an intervention on this counterfactual SCM. And then I would just propagate through with these new equations, right? So now I would know, well, okay, I sample this always, or I guess this is the guy whose equation is getting replaced in the intervention. So if I set that equal to 1, then I can solve for each of these. And I'm going to get like a Newton-tailed distribution over x1, x2, x3, x4, and x5, where basically all of them are going to be shifted up by 2. And if I were to change any of these initial values, we'd see like kind of corresponding changes in those counterfactual values. So I have a few things about that, some pointers to literature in the readings. And then I also have some pointers for people who are interested in structural causal models where you do allow for cycles in that exogenous graph. And also kind of more interpretations of what this latent projection operation means and things that it doesn't kind of capture. So it's a kind of lossy operation, at least in the case of kind of general graphs. If we're thinking in Markovian models, it's a very good operation. We don't lose anything by doing that. So that's all for today, and hopefully y'all are around for the next 7 lectures. Thanks.